That there was a 1-to-1 ratio for the.
Yeah. Y'all ready to answer some questions? Or ask some questions? Yeah, what's up?
What homework are we supposed to be on right now? That's on the midterm.
So which homeworks are on the midterms? I'm pretty sure it's homework 1, 2, 3. And have we started homework 4? I might be getting the classes confused.
It says 5 and then 4.
Oh, it's numerical order. That's probably just a.
Well, I felt like homework 5 is stuff that we did the other day, and homework 4 was
I would have to look at those. What was homework 4?
I don't know. I can tell I just don't know. Or is it just like homework 3 we're supposed to know? Or?
Well, it's homework 3 and the next one, which I thought was homework 4. Yeah. So I'm pretty sure homework 4 is a lot of definitions that we should be able to figure out from the other parts we've done, from definitions of titrations and some of the other concepts. And the homework 5 is actually the calculations of titrations. Okay. I did the material in class a little bit out of order. We did the titrations first. Homework 4, a solution of weak monoprotic acid prepared. Yeah, that's an equilibrium. No, these are the same calculations we've been doing.
And then homework 5 is like the next
tab over. Homework 5. So homework 4 and homework 5 are almost identical. The difference between homework 4 and homework 5 is, so technically both. We could be doing both. So homework 4, but we'll just stick it to the beginning. We'll do 1 through 3 in part of homework 4. So homework 3 is focusing on the acidic calculations, weak acids, which is where we typically start with our titrations. And then that's homework 4. Homework 5 is doing the weak base titrations. And if you do all of homework 4 and all of homework 5, you're going to go, oh, it's all exactly the same. All the calculations are the same. You're just doing it with KBs instead of KAs, but everything else. And you're calculating POHs instead of PHs, but everything is the same. All the calculations. The calculations we did Monday in class, those are all the calculations we have to do. We're just going to introduce the Henderson-Hassebach equation to make it a little faster. I decided I don't really like the Henderson-Hassebach equation because it hides all of the stoichiometry and all of the equilibrium phenomena.
Oh, that'd be terrible.
Right? If you just hid all of the stoichiometry and all of the ice tables in one equation and didn't have to do them anymore, it's the worst. So, well, I mean, it's fantastic. It's fantastic. But the thing that drove me crazy about it is students would memorize the Henderson-Hassebach, they'd find it on the equation sheet, and they'd be like, great, I can do the Henderson-Hassebach equation for everything. And it's like, no. You have to understand when you can and cannot use it based on how it's functionally created. They're like, but it's on the equation sheet. It's like, you have to understand where the Henderson-Hassebach equation comes from so we can understand when we can and cannot use it.
So it's like all of homework 4 and 5 we should know that stuff?
Let's say most of homework 4. I haven't looked at homework 4 to see entirely, but I'll check before class and have an answer for that by the end of class.
Sorry,
question.
So maybe we should just focus on like homeworks 1 through 3.
1 through 4.
1 through 4, okay.
1 through 4. And it's just a matter of how far through 4 we get, which I think we should be able to do almost all of 4 already.
After today, or
already.
Okay.
I think the only parts of 4 that would be challenging is because we did math on Monday instead of concepts. Some of the concept questions and the term definitions might seem difficult. This is what a textbook is for, right? If you're like, if the problem asks you to calculate the midpoint, and you're like, well, we didn't define that. It's a term, you can look it up. Okay, but at the same time, still, we're going to go over all of that in class. Like, I'm not saying, like, oh, get another textbook, I'm not going to bother. Like, no, of course I'm going to help you out with that. But at the same time, I think you're all completely capable of figuring it out as well. So, I'm here to help you figure it out, but I bet you could figure it out if I wasn't here. It's just who would tell you to. Other concept questions, idea questions before we get to specific questions? Yeah.
Can you talk about the difference between the midpoint and equivalence point?
Yeah, so this is actually a definitional thing we're going to get into today. And when we're looking at weak acid titration curve using a strong base, you essentially end up with something that looks like this, right? And we did the calculations, actually, to calculate this entire curve, but we haven't defined which part of the curve we were calculating. So the midpoint is the halfway point, and the equivalence point is the whole way. So this is like 50%, and this is like 100%, or this is half weak acid reacted. This is all weak acid reacted. And that's it. So the nice thing is, and again, we're going to talk about this today, and we'll be talking about this curve and how we use it all next week as well. So if you're like, whoa, I don't understand this yet, that's okay. We're just getting started on it. But what we're going to find out is, essentially, if you can calculate the moles to this point, cut it in half, that's the moles to this point, right? The x-axis is essentially going to be like a stoichiometry calculation, but then this axis, which is pH, you don't have any simple relationship like that, because this is all equilibrium calculations. And we'll get really fast at titrations before the next midterm. So there'll be lots of titrations on the next midterm. Question? Yeah.
I have a question. Like understanding pH and pOH. Do you use pOH when it's a strong base, or when do you use pOH?
When it's convenient. So the thing to remember is we can always use either one, because we have this relationship in water. Right? The equilibrium of water, the autoionization of water, essentially gives us this definition, which we can write a few different ways. We can also write this as H3O plus concentration times OH minus concentration equals 1 times 10 to the minus 14. And then we could also write this as Ka times Kb equals Kw. And we can also write this as pKa plus pKb equals 14. All four of these equations are all from the autoionization of water, the behavior of weak acids and weak bases in water. And this is for a conjugate pair. And then this is also for a conjugate pair. Right? It's not generically any Ka is related to any Kb, but for a conjugate pair we have this relationship, and we showed that by writing down the concentration expressions for those. So really, we could talk about pH or pOH at any point in the curve, at any time. If we've got a pH, we can also find the pOH. It just becomes a matter of what's more convenient to talk about. We almost always convert to pH because that's the more commonly used scale. Like if I say, oh, it's a pOH of 5, people don't have a kind of intuition of what that means. But if I say pH 5, you're like, oh, that's acidic. That makes sense. So it's just what people are familiar with, so we almost always go to pH. But in our calculations, sometimes it's more convenient to calculate pOH. When we're dealing with weak bases and we have OH minus production, it becomes easier to write down the pOH and do a calculation with pOH, and then convert it to pH for the final answer. Was that good?
Yes.
Cool. Other concept questions?
What do all those relate?
These are all related to the water equilibrium and how weak acids and weak bases behave in water. Right? The number 14, the Kw, that all comes from autoionization of water. It's all the autoionization of water. Which also explained why water is neutral at 7. Right? That's because water has an autoionization. You end up with a pH of 7. Question?
I had a question about the bond length and like correlation to
Acidic strength? Yeah.
Like, what's the correlation?
Right. So it depends on which. Where did I put my eraser? So it depends on which category of acid we're looking at. So we've got 3 categories of acids that we consider. We have oxoacids. We have
Metal hydrides.
and we have so in these different situations we have different molecular structures that are giving rise to the acidic and basic behavior. So the thing we have to consider in order to make sense of this is in which cases is there a variation in bond length related to the acidity, in which cases there is no variation in the bond length related to the acidity. So when we look at something like oxoacids, we always run into the situation where if we looked at sulfuric acid, which is an oxoacid, I almost put phosphoric. We got SOOH, OOH. We've got an oxygen-hydrogen bond length. If we look at acetic acid, we got CHHH, COOH. We've got an OH bond length, right? So in oxoacids, we're always dealing with an OH bond length for where our acidity is going to occur, right? The acidic proton in this case is here. The acidic proton in this case is here or here, but all of them are OH bond lengths. So in that case, the variation of the bond length isn't going to exist. It's not going to matter. If we look instead at metal hydrides, we're looking at a case where I'm just going to do a generic. Let's say we've got some M2+, we've got some oxygen attached, we've got some waters attached through oxygen. And pretend I can draw three-dimensional. Let's keep going. Right? And if we look where the acidic proton is, where is it? Does it matter which one we pick? All of them, any one of them, right? All of these hydrogens are essentially equivalent in this case. And all of them have the same approximate oxygen-hydrogen bond length. In this case, what matters is what's the size and charge of the metal at the center. In this case, it's how many oxygens, what's the electronegativity versus the number of hydrogens. Both those cases, the radius doesn't really matter. So it's when we go to the non-metal, sorry, why did I write? I got these backwards. Oh, so embarrassing. It's on video too. Sorry, everyone watching. That was embarrassing. So, metal hydrates, water's hydration, right? Non-metal hydrides, that's going to be stuff like SHH, HCl, HBr, and notice I wrote these to kind of cartoonishly exaggerate the fact that we do have this bond length dependence. So in this case, the hydrogen is bonded to a different element, and that difference in radius of the attached element is going to give a different bond length. And in that case, we're going to see that that bond length change is going to give rise to a change in the acidic behavior. Does that get at what you were wondering about?
I think more so like with the non-metal hydrides, like would like HCl in comparison to HI, would it be weaker acid?
HCl would be, say it again?
Weaker?
Yeah.
Because the bond is shorter?
Yeah. Now, the problem with this trend is we know that it's going to be weaker, but we really don't know how much weaker, right? That's where we would want to use the Ka value to specifically say how much weaker. That is because in this case, we've got two things that compete, right? We've got the bond length, but then we've also got the electronegativity. So I can't just look at this and be like, oh, the bond is twice as long, the acid is twice as strong, right? Because we've also got that shift in electronegativity, which is going to change it as well. So this bond length is smaller, but chlorine is more electronegative, and those two things will compete. That's why we get this funny situation where HF is actually not a strong acid. Even though it's a very powerful acid, it's a very dangerous acid. the bond length is so short that it doesn't 100% disassociate. So we don't consider it a strong acid. It's K, but still, the Ka for hydrofluoric acid is something like 0.98. It's like, or maybe it's 0.89, something like that. You know, it's just below 1, but it's still like almost completely it's very disassociated compared to our typical weak acids. So it feels funny to call this a weak acid. I usually say, well, it's not strong, but it's a very, very good weak acid. Yeah.
So what are like the rules for the two other ones, like with the relation to the hydrogen, like the more hydrogens it has, it's like stronger, weaker? Like I don't know, that's what I'm asking.
Okay, so this is something that we can review. So these definitional things, it's very, I can always explain them again. I'm always happy to explain them again, but it's also one of those things where we also have to read the definitions and review them. Because it's definitions, right? So we can also think about it logistically, right? Like what gives rise to acidity? What makes it so we have an acid? Based on the Bronsted-Lowry definition?
Like an acid donating a proton.
Donates protons. So ultimately what we're doing in all three of these cases, regardless of what category we're looking at, all we're really looking at is which thing can donate protons more good? Which one donates protons better? And then we have to say, okay, so what's going to give rise to better proton donation? In the nonmetal hydrides, we say, okay, longer bonds are easier to break, approximately, and higher electronegativity is harder bonds to break. So we've got that kind of push-pull of longer bond versus electronegativity, and it turns out, at least when we're going down a column, the change in bond length is usually more dramatic than the change in electronegativity. So in this case, we're looking for the longer bonds versus the electronegativity. If we're going across, the electronegativity change is more important because the radius changes very little. So we're looking at that composition of how easy is the bond to break. When we're looking at our metal hydrides, so it's for metal hydrides, it's bond length versus, why is it squeaking so much today? It's driving me crazy. So for metal hydrates, for non-metal hydrides, it's bond length versus electronegativity, with bond length being a little more important. When we go to the metal hydrates, we run into this problem where like, oh, all the bond lengths are the same. Oxygen's there, that electronegativity is the same. So it's really going to matter what the center metal is, right? And we're looking at two things. We're looking at how much charge the central metal has, because that's going to be essentially taking that's going to be drawing electrons away from the hydrogens and making the hydrogens easier to pop off. And we're going to be looking at how close all of this can get. So when we're looking at this combination of the size of the central atom and the charge of the central atom, we call that charge density. I'm going to go visit Paul and get some tools and just fix it, but after office hours. So we look at this idea of charge density. For the oxo acids, there's a little bit more flexibility, and like it's not really just like a one set thing, right? Again, it all is fundamentally how difficult is it to break that bond? How well can that proton, whatever acidic proton we're looking at, how well can that proton be donated to another compound? In most of these rules that we're looking at, we're doing donation to water, right? We're looking at how this behaves with other water molecules. Remember, with the Bronsted-Lowry definition, it's just proton donation. Well, what else does it donate to? We're doing water. So we look at this and we say, okay, what gives rise to making this bond more breakable? What makes a weaker bond? So anything that's going to remove the electrons from being close to the hydrogen is going to make this bond easier to break. So what we really look at is, where's the electronegativity relative to the hydrogen I'm looking at? And does that motion of electrons away from the hydrogen make the bond easier to break? Or, I mean, how much easier does that make the bond to break? So ultimately what we're looking for is a distribution of electronegativity, right? And in the oxoacids, that is predominantly going to be where are the oxygens. Oxygen is very electronegative. The only thing that beats it is fluorine, but fluorine doesn't bond with many things. So in all of these cases, we're just saying where are the oxygens, how many electrons does the oxygen have versus how many does it want? Like where is that electronegativity towards relative to the hydrogens? So typically in oxoacids, the rule that you'll get out of the textbook, the kind of guideline that you get out of the textbook is ratio of oxygens to hydrogens. If you've got, or like the difference in the number of oxygens to hydrogens. So like in this case, you got 2 oxygens and 1 hydrogen. That's going to be, a weak acid. Here you've got 4 oxygens, 2 hydrogens. It's still a 1-to-2 ratio, 1-to-2 ratio. So both of these are pretty good acids. This one is better because then you also, in addition to the number of oxygens, number of hydrogen consideration, you also have to think of the electronegativity of the thing in the middle. Since sulfur is more electronegative than carbon, this is essentially another thing that's going to pull electrons in. So the sulfur and all of the oxygens are working together to pull the electrons away from the hydrogen, versus here it's just the oxygens pulling from the carbons and the hydrogens. So we have to kind of like do that puzzle thinking. Generally, we can say how many oxygens versus how many hydrogens. What's the electronegativity of the central metal? Or the central atom. It gets more tricky when we start going to second protons, because once you get rid of one of those hydrogens and this becomes an oxygen with a minus charge on it, that has very different electronegative behavior than an oxygen without a minus charge on it. That negative charge essentially takes care of or neutralizes or balances out the energetics for all of the electronegativity of that oxygen, so it essentially erases that oxygen. And now you have to say, okay, now we're holding on to this, essentially. But, it essentially balances out that oxygen. But more, it's like, now instead of trying to pull electrons from a hydrogen, this electron is going to be pulled by all of these things, and it's going to essentially be distributed, right? And we're going to get into this later in the quarter, where these simplistic, like Lewis structures, they're nice cartoon, like starting points to talk about atoms. But as we know from 127, we should be really doing like electron cloud distributions. Where are the electrons in terms of where they're likely to be? Not like, hey, there's 4 electrons here. Like, electrons are not static objects. But it works for a quick cartoonish picture. Good? Yeah.
I need to take the quiz from last week.
For
129.
Okay. Oh, right. You were out of town.
Yes.
Okay.
It doesn't have to be right now, but.
Okay. We'll get to it.
Okay.
Other questions? Do we have any more concept questions, or should we get to homework? Yeah.
Just a quick question. Will we be asked know which one's more acidic between the different categories?
No, it becomes really difficult if I give you Kas, yes, right? Because that's just comparing the actual equilibrium constant. But if we're doing qualitative comparison between categories, that becomes really difficult. The only place where that becomes less difficult is if I put HCl up here with a bunch of weak acids. HCl is strong. It's going to be the strongest, right? So there's some things where it's like it looks trickier than it is because I'm mixing in some I'm doing a non-metal hydride with oxo acids, but HCl is a strong acid. So if the other 3 are weak and you're organizing them, HCl is going to be the strongest. Generally, I'll stick to one category at a time.
Okay.
Generally. Other questions? Should we get to some homework stuff? Great. What homework questions are we working? Homework 3?
Yeah.
What questions do we have from homework 3? Just number 3? Oh, okay. I was like, wow, the rest of the homework was okay?
No.
No.
Specifically HC.
8C.
12E. Although it's like a multi-part and it flows into it pretty easily.
Okay.
13.
Grant, yeah.
You gotta just do a random number generator and be like, how
That's what
about
I was
number
thinking.
9?
You could do number 9.
Why not?
Let's get ones that people actually have questions
Okay.
on first.
We also look at worksheet questions as well.
Yeah, we can look
later.
at worksheet questions. Yeah.
I need to go over them still a little bit, but
Gotcha.
I'll come back to you.
Yeah. And I also have office hours tomorrow.
You do?
You do.
Yeah.
What time?
2 to 4.
Oh, I didn't know that.
It's on the syllabus.
Oh.
Well, is
I
it
sort
for
of stopped at Wednesday.
one of your other classes or?
No, so Wednesday's like my 129 focus, but you can still come by and ask, like you can all be here. Thursday's open. And then Friday is my 124 focus, but you can still come by and ask questions. Like I've got some 124 students here today too. And the only reason I'm doing that, this is the first quarter I've tried doing this, and it's mostly just so I can do I can make a video for 129 and not have to have it like, oh, this video is half 129, half 124, and like skip around to get to the question you care about.
So 2 to 4 tomorrow as well.
2 to 4
Right.
tomorrow. Yeah.
Okay.
Who's got the homework handy? Oh yeah. 14. Who's got the homework handy and can read
I do.
number 3?
The measured dissociation of an unknown weak acid is 3.2% when its initial concentration is 0.2 molar. Sorry. A. Calculate the H3O OH concentrations, pH, POH, and unknown anion concentration.
And
The unknown anion.
so we'll call that just anion A minus.
And then there's a part B. Do you just want to go to A first, or should I say B?
What's B?
Okay. B says, what is the Ka of the unknown acid?
So I like going to part B. Well, so did this totally stump most of you?
Yeah.
So what's interesting about this is it's really just a definition. What is percent dissociation? Let's make it easy for a moment. Let's say I've got something that's 1 molar, and it's an acid. It's some HA, and it 100% disassociates. What does it become?
0? No,
Well,
I'm confused.
we know it's going to go to H plus
Oh.
and A minus. But what's going to be the concentration of each of those if it 100% disassociates? 1 molar. Right? Because it completely disassociates. That would be like a strong acid. Let's change it and say, what if it was 10% dissociation?
0.1.
Now let's go ahead and change it again. Instead of 1 molar, what if it was 0.1 molar? And we had 10% dissociation.
0.01.
Right? Notice the percent dissociation is telling me the H3O plus concentration and the A minus concentration. So I can look at this and not setting up an ice table, just using the definition of dissociation, I can look at this and I can immediately say H3O plus is equal to 0.032. That's my 3.2% times 0.2. That gives you your H3O plus and your A minus. You take the negative log, that's your pH. 14 minus pH gives you your POH. 10 to the power of POH gives you OH minus concentration. We can do all of that, but just notice the only real tricky part of that was understanding the definitional idea of what percent dissociation is. So in terms of the math, we do 0.032. After we get that idea, the rest of the calculations are suddenly like, oh, this is easy. And this is one of the main things we have to work on, is that kind of concept-driven problem analysis. How do we pick apart a problem? How do we make sense of a problem? How do we get what the problem's trying to get us to figure So let's see if I can do this in my head. 64.0064.
Oh yeah, for sure. No problem.
So I just moved my decimal place
Yeah.
over, multiply that by 2. 0.0064 molarity. That is going to be equal to essentially my X, which is going to be equal to my H3O plus, and is going to be equal to my A minus. So H3O plus is 0.0064, A minus is 0.0064. I take the negative log of 6.4 times 10 to the minus 3, and I get what, like 2.8? I've started getting good at logs. Have I got good at logs in my head?
2.19.
2.19. Oh, because it's almost 1. Yeah, I always got the wrong direction. So 2.2, but I thought 2.8. I'll get there eventually by the end of the quarter. So we can take pH equals negative log 0.0064, and we get 2.2. Then we can say pOH equals 14 minus pH, which is going to be 11.8, if I can do math in my head. So I guess it's 12, 14, yep. And then OH minus. Now notice there's actually, for these two steps, there's like 3 different ways we could have done it. Right, we could have taken our H3O plus concentration and converted that to OH minus concentration. That would have been totally valid. We could go through pOH to OH minus. That's totally valid. I think actually those are the only 2 ways because we don't want to get into KBs with this one. But again, using the equilibrium of water, there's 2 different ways to solve this. I did it the way that's a little bit longer, but I think a little bit more story-driven. OH minus is then going to be equal to 10 to the minus 11.8, which is going to be 8 times 10 to the minus 11.
I got 1.5 times 10 to the negative 12.
Okay. Again, I'm going
Ballparking it.
I'm going the wrong direction. I was like, I know it's close to 12 because 11.8 is almost 12. But I always go the same thing here, right? I was like, I know it's close to, oh, I should have gotten this one right. That should have been close to 3. But it was actually close to 2 because 6 is like on the 2 side. And I like, yeah, but trying to do logs and 10 to the powers of in my head is not always a good idea. So I'm glad you all have calculators. So that's everything for this. Now, we can go to part B. Can you all do part B though? You're all nodding yes. Take a moment, do it. Let me check. Is everything lined up? You can see everything? Yeah, great. Okay. Yep. Do we need to make an ice table?
No,
Why not?
because we have all of the concentration.
Yeah. So we can say Ka is H3O plus, A minus, HA. And also notice we don't actually have to do 0.2 minus 0.0064. You can. We don't need to use the x is small approximation, right? Because we are given the x value. Right? We can exactly calculate all of these numbers. But if we use the x is small approximation, we're just going to use the initial concentration of HA rather than the equilibrium concentration of HA. If we wanted to use the x is small approximation. So we could say that this is exactly equal to 0.0064 times 0.0064 divided by 0.2 minus 0.0064. Or we could say that's approximately equal to 0.0064 squared over 0.2. The reason I wrote it particularly that way is because notice this is x squared over HA initial. Right? And every time we've done a weak acid in water, we've always gotten Ka is equal to that. Either way you want to do it, the approximate's good enough. If you do it exact versus approximate, you're going to have like a 0.1% error.
Yeah, it's like 2.12 times 10 to the negative 4, or 2.048 times 10 to the negative 4.
It's a bigger error than I was expecting. But still, it's a relatively small error. Cool. So that's number 3. What's up with number 8? Any questions on this before I erase it? Okay.
So number 8 was consider the acid-base indicator bromothymol blue, which dissociates via the following reaction, which it uses the shortening HIND.
Okay.
And it just breaks into H plus and IND minus aqueous ions.
I want to use blue, but all my blue pens are empty. There we go. So we got HIND to say, hey, that's an indicator. Breaks into, I'm going to call it, does it do H3O plus?
It does H plus, but that's
Let's
fine.
do H3O plus is more correct, right? IND minus.
So A asks, what is the Lewis structure for bromothymol blue? Which protons are acidic? And
That's
it's
just
a really big structure.
It's a big structure. That's like just look it up, right? That's not something I would ever ask you to remember. The more important part there is identifying which protons are acidic. So let me ask this in a general case. Do you have this structure?
I can pull it up.
Everyone look up the structure of bromothymol blue real quick if you've got some digital device connected to the internet, if you're watching at home. What I want you to notice is which protons do you think are acidic, and most importantly, what category of acid is bromothymol blue? And before you answer, let everyone else kind of take a look. Bromothymol blue.
What are we supposed to be looking at? The acidic protons?
Yeah, which protons do you think are acidic? And the thing that I'm really curious about is which category of acid is it? Metal hydrate, non-metal hydride, oxoacid. Are there any metals in the structure? No, so it's not a metal hydrate. Are there hydrogens directly connected to nonmetals? No. So it's an oxoacid. There's oxygens, hydrogens. Not all of the hydrogens are acidic. We're looking for those hydrogens that have the most electronegativity next to them. Those are going to be the most acidic. But I'm not going to draw the structure right now. But you can identify, oh, those look like the acidic protons. That's part A, right?
Mm-hmm.
What's part B?
Part B says, should you add acid or base to make the solution appear darker blue? When it's dissociated, it becomes bluer.
So this is like the blue one. This is like the yellow version. So we can logic this just from the Chatelier's principle. If I add H3O plus, which direction does the equilibrium go? If I add acid, it's going to shift towards being more yellow. If I add base, which way does this shift? Now there's no OH here, but the OH minus we add will essentially remove H3O plus. If we remove H3O plus, the reaction has to go towards the product side, as written.
Can you repeat that?
So essentially, if we add H3O plus, Le Chatelier's principle says we're going to go towards reactants. It's going to become more yellow. If we add base, the base is essentially going to do a reaction. If we do OH minus, the OH minus and the H3O plus will react to form H2O. So essentially, adding OH minus is the same as removing H3O plus.
Mm-hmm.
And if we remove H3O plus, the equilibrium needs to shift toward the right. So that's going to become more blue. And if you get it perfectly balanced, where you've got 50% indicator, 50% protonated, you'll have a green color. You can make this also become green. But we'll do that when we talk more about buffers after the midterm. H indicator, indicator. So that was part B, was just like which way do we shift? Adding base will shift it more blue. Part C.
Yeah, part C you kind of touched on just now was how do the values for K for this reaction compare for a yellow solution, a green solution, and a blue solution with different amounts of acid or base added?
This is a fun question that's really reviewing something you did in Chem 128. Do you remember the determining the equilibrium constant lab? I should say it differently. Hey, you all remember the equilibrium constant lab you did in 128, of course?
Yeah.
Of course, of course. So that was the lab where you had to make the blue solutions and the yellow solutions, and you had to make your two curves. And then you made a green solution, and you're like, oh, you were trying to find the equilibrium constant, and you were doing it actually for bromothymol blue. And the thing that messed with everybody was they thought the green solution was the one at equilibrium. Let's think about what equilibrium really means when we're looking at this. Can you have equilibrium where it's all yellow? Yeah, if we add a bunch of acid, the equilibrium will shift, the reaction will stop, and it'll be mostly yellow. What's the Ka in that situation? Does the Ka change when I change how much of each material there is? What's the name of Ka? What is Ka? Like, just the term that we call it. What's any K?
It's an equilibrium constant.
Equilibrium constant. So, if I add a bunch of H3O+, is that going to change the equilibrium constant? It'll change the equilibrium, but not the constant, because the constant is a ratio. If I add a bunch of base, will I change the equilibrium constant? No. If I'm adding different amounts of products and reactants, does the Ka for this thing change? No, the Ka is always the same for this, right? So conceptually, part C is really just saying, no, the equilibrium constant is constant. It's the same regardless of what color the solution is. We can describe the color of each of these solutions by looking at the Ka and looking at the ratio of products to reactants. That's what the Ka allows us to do. Now, if we wanted to go back and review Chem 128, we could say, oh, what factors do change the equilibrium constant? We can say, okay, temperature will change the equilibrium constant. So there are situations that can change the equilibrium constant, but at the same temperature, it's going to be the same for each of these solutions. It's just we're adding different equilibrium condition for each one. Basic, acidic, middle. But the Ka is the same in all of those conditions. Was there a part D to that one?
No, that was it.
Cool, that was it. So that was problem 8. Again, concepts, definitions. This is the part that's really challenging about Chem 129, is so many people get hung up on like, I gotta do calculations. And yeah, it's important to know how to do the calculations, but none of the calculations are actually that hard to do. They're just time consuming, right? They're all the same math. We've been doing the same math for 4 weeks now. The concepts, the ideas that the math is explaining, that's the important part, right? And this was like almost every question we've talked about so far in office hours today have all been concept questions. Have all been idea questions. 12.
Okay. So that's the polyprotic acid, malonic acid. So C3O4H4. How does the acidity and basicity relate between the protons? And it's got like an A through E for these. Right. A is right down the
Malonic acid, if I remember correctly, is COOH. HHCO. Is it a cat?
Yeah.
Double carboxylic? Yeah, okay. So that's malonic acid. Where are the acidic protons? Is it these middle two? You should all shake your head no violently. No, of course not. We want the protons that are attached to hydrogens. We want the things close to the electronegativity. That's where we're going to see our acidity. So that's part A. Part B.
It says, what is the Ka expression and value for malonic acid?
Ka. I'm going to... Oh, chemists, don't get mad at me, but I'm going to go ahead and call this H2 mal. Just to kind of shortcut writing this all out. So if I write Ka1, I'm going to look at losing the first proton. Which proton should we lose first? Doesn't matter, right? It's just one of them is going to be lost. These protons are essentially identical. So I'm going to have H mal minus, H3O plus, H2 mal. Where when I say mal, I'm talking about C3O4 H2 2 plus, right? Losing both of those underlined hydrogens.
Can we write that on the midterm?
H2 mal?
Sure, like any.
As long as you define what you're using as your shortcut, yes. Right? I had someone on one of the quizzes, I was like, write the equilibrium expression for this acid. They just wrote HA. And I'm like, it's not wrong.
Should that be 2
It's
minus?
not. Oh, yes, that should be 2 minus. You're just doing generic like HA. It's not wrong per se, but it's not specific enough either. So as long as you define your shortcut, yeah, you're okay. So that's the Ka.
Yeah, that's part B. Part C is the Kb for the conjugate base of malonic acid.
I'm going to call that Kb1. And we're just going to do H2 mal, OH minus, H mal minus. So what we're essentially looking at here is how well does this donate a proton versus how well does this accept a proton, right? And that's going to be mediated by water. That's why these two relate to each other through Kw. But yeah, we can look at that. Are you having trouble seeing that in here? So let's write the reaction. So this is H2 mal goes to H3O plus H mal minus, or I can look at H mal minus goes to H2 mal plus OH minus, with of course water in there as well. So in this case, I'm looking at how well H2 mal donates a proton to H2O. In this case, I'm looking at how well H mal minus accepts a proton from H2O. Right? Almost opposite of each other, but not exactly opposite of each other because we're also changing the behavior of water in those cases. We also notice, if that seems really weird, we know that there is like an inverse relationship to this, right? The better this thing donates a proton, the worse this thing accepts a proton, adjusted by water. Okay.
Part D asks for the Ka expression and value for monoprotic malonic acid.
So that is where we get to Ka2. So now we're looking at how well does it, after it's donated one proton, how well does it donate the next proton? So we're going to look at mal2 minus, H3O plus, over H mal minus. And we're going to look at K, I assume we're going to look at Kb2 as well?
It actually doesn't ask for that.
Okay.
Yeah. Part E asks, what relates the first Ka to the second Ka?
So there's a couple ways we can think about this. In terms of having an equation, so it's nice that Ka1 and Kb1 relate to each other through Kw. There's no equation that relates Ka1 to Ka2. There's no mathematical relationship that we can easily write down. So what does relate the two?
The conjugate base from Ka1 becomes the acid for Ka2.
Yeah, that gives us a way that they relate. So what's the similarity what is the same between those two? I'll give you a hint by erasing this and putting a minus charge there. It's the structure.
Yeah.
Right? If you were like, this seems too simple, it's the structure. The structure of the compound, the Lewis structure, where the electronegativity is, what the charge is, how far this other hydrogen is from that, how much that balances out the attractive forces. All of that goes into explaining how these two relate to each other. But again, there's no simple mathematical relationship between the two. It's a structural relationship, not a mathematical relationship. So that's the idea that it's trying to get at. I would say most of those questions, since they were just asking you to write down equilibrium expressions, were fair. That last one probably would be post-midterm when we start talking about polyprotics.
Got it. So we're
So,
probably not going to see that one
12E,
coming up.
getting into the actual concepts with polyprotics, a little bit beyond what we're doing this time, but definitely something that, you know, everything else, just writing down chemical reactions and equilibrium expressions, we should be able to do that. Identifying which protons are acidic, we should be able to do that. 13, are we ready to move on? Any questions on this? Okay, problem 13.
You have an acid solution with a set volume, pKa, and pH. So I'll give this to you when you're ready. Or
What is
not,
it ultimately?
Not set, but it's
Given.
Yeah, given.
And it's trying to get us to find.
The concentration.
Okay. So we have pKa.
5.45.
We have
pH 3.
We have
volume 250 milliliters.
I don't even know if we need volume.
Yeah, there's a part B that I think.
Oh,
uses
okay.
But part A is just find the concentration H3O plus.
Oh.
Yeah.
H3O plus
log.
negative log of pH.
Yeah. So
part A is just H3O plus equals 0.001.
Yeah.
Okay, I can do 10 to the minus 3 in my head. I can do that one.
Okay. Part B says if you're going to make a solution with the same concentration that has a pH of 2, what should the pKa of the acid be? And then it asks what are some acids with the possible pKa values. Use your appendix to find them that are similar.
So I want a pH of 2. I want the same concentration. Ask for the concentration of H3O plus. Does it ask for the concentration of the acid?
Oh wait, sorry. Yes, the acid.
Oh,
my mistake.
Yeah. So it's asking for the initial concentration of the acid. It's asking us to also find HA, right? HA initial. So if we wanted to set this up, we could write down a generic ice table and all that stuff. But again, we've done this enough that we know we're going to get Ka equals H3O plus squared, right? X squared divided by HA initial. We've got the Ka, we've got the H3O plus because we can turn the pKa into a Ka. It's going to be 5.5 times 10 to the minus 6. Still can't do logs in my head.
I got tripped up by this one because I got just concentration H3O plus. I didn't read carefully enough.
Okay.
So I gotta do this
Yeah,
calculation later.
that would make part B completely impossible.
Yeah.
Right? So you need this HA. So essentially what we're doing in this problem is, in a lot of these problems, we've got 3 possible variables. We've got our Ka, our H3O plus, and our initial concentration of acid. In part A, we're given 2 of them, and we're asked to solve for the third. In part B, we're given 2 of them. We're given these 2, and we're asked to solve for the third. So in terms of problem solving, after we identify the right equation to use, it's just a matter of determining which variables we have and which variables we don't have in order to solve for the missing bits.
So to go from pKa to Ka, we just do the 10 to the minus whatever.
Mm-hmm. 10. Don't forget your negative sign. 10 to the negative 5.45. And that should get us between the two.
Why is the H3O plus squared?
Because remember, if we're looking at a generic acid, HA goes to H3O plus A minus. We've got our initial, we've got 0, 0, minus X, sorry, plus X,
Right.
X, X. Because of the 1-to-1 ratio.
Oh,
I
you're
just took a shortcut.
summarizing. Okay.
Right, yeah.
It's not actually.
Yeah, so this is technically, this should be H3O plus times A minus, but those have the same concentration, so we can just call this X squared and say that that's equal to X, if you're more comfortable with that.
Yeah, it's just
I like
bigger
writing
than
it that way a little bit more because then it falls, it's like, oh my god, this is so exactly what we've been doing. Right?
I got the acid concentration as 3.548, the initial.
3.548?
Because you divide by the. Oh wait, no, I forgot to flip it.
Oh, so 1 divided by 3.548,
Yeah,
so about
1 divided-
0.33?
Yeah.
Probably like 0.302 or something like that.
Yeah, 0.28.
There we go, 0.28. That makes more sense. Whoa. I was like, oh man. Okay, so 0.28. So that means in the second half, we've got the pH, which is essentially giving us X equals 0.01. We've got the HA initial because it says I want my acid to have the same initial concentration of 0.28. And now we're trying to find Ka. So we're just switching which variable we're solving for. This kind of logic is what lets us do problems forwards and backwards. Right? We can go both directions in our calculations. I'll let you finish that calculation on your own, and we'll move on to number 14. Who would like to read number 14? Somebody else, if anyone's got it handy.
When a salt is dissolved in water, what properties of the ions produced will result in an acidic solution, a basic solution, a neutral solution?
Okay, so what salt dissolved in water would give acidic solution? So in general, a salt is a metal cation with a non-metal, I don't know how to represent that, we usually do X, we'll do like a non-metal anion, right? So, what would give rise to an acidic solution? Let's do basic solution first. Basic solution is pretty easy to do. What's the simplest example of a salt that would make a basic solution?
Anything with hydroxide.
All of our metal hydroxides would do that, right? What else would do it? Any metal with a conjugate base of a weak acid. Any metal, we'll just say any metal with a conjugate base. No, we have to say weak acid, right? Any metal with the conjugate base of a weak acid, put the of in there as well. Any metal with the conjugate base of a weak acid, since you're putting in essentially a base, that would also make it basic, just less so. This also explains how we can get something that's neutral. If we want to do neutral, we're going to do a metal with the conjugate base of a strong acid. Right? Example of this that would be neutral. What does everyone think when they think salt? Oh, not hydroxide. Sodium
Oh.
chloride. Sodium hydroxide would be like over here. Sodium carbonate could also work over here, right? So sodium hydroxide, the hydroxide would give us that example. Sodium carbonate, that's the conjugate base of a weak acid. Sodium chloride, that's the conjugate base of a strong acid. No pH effect. I'm having a little bit more trouble thinking of what would give acidic solutions. We could do something, rather than doing our typical metal salt, we can do something a little bit different. I'm thinking of one example in particular, and we had this one in one of our examples in class. We had NH4Cl, ammonium chloride. This is the conjugate acid of a weak base. Right, so that would give us acidic properties, right? Having the conjugate acid of a weak base in our salt would mean essentially we're putting an acid into solution. And we had that in one of our examples in class.
Got it.
I'm trying to think of something that fits the typical salt, metal, non-metal combo, but
Are they just not so common?
no, and I'm trying to think if you had a metal that would form a metal hydrate, that could do, right? Because then you're putting a metal hydrate. Metal hydrates act like acids.
Right.
So there's some other weird examples we can come up with to make it acidic. But this is the typical, right? This is what we would actually see in like the chemical world on a regular basis. There's some other atypical ones we can think of. So like a chromium chloride, if the chloride's disassociated and water's associated, you form a metal hydrate, which would have acidic properties.
Right.
But that gets into metal complex formation, which is our next subject after we finish acid-base. Because that's a little bit more complicated than just being like, oh, metals and water, right? We have to talk about how those complexes form and the properties of those complexes. And we'll get to that. Not on this midterm. Maybe not even on the next midterm, but we'll get to that.
Got it.
That's pretty much number 14. Is that all number 14 was?
Yeah.
Cool. Again, no calculations, just concepts, right? Definitions, ideas. There's plenty of stuff we can do calculations on as well, but the concepts and definitions, those are the big things. Other questions? Okay, I'm going to stop the video. I'm going to stop the live office hours. Sorry, everyone who's like, but I got questions, or anyone who shows up late. These have only been going for an hour, so. But I'll stick around and answer more questions. And I'll post this video right now.